Good afternoon mga Bisaya. Um, so it's been a while since I did our last video about the foundation. Um, I- I'm really busy at work, and then it's also camping season at the same time, riding season. So it's really hard to find time to do these videos. But anyway, so our topic today is about minimum pile length. So that is with or without lateral load. So um, the things to consider in determining the pile embedment is, well, we have at least two considerations. One is embedment uh, due to axial load. So if you have compression and then uplift, uh, so if this is your pile, so it is subjected to a compression load or tensile load, then we will have a minimum embedment based on the bearing skin friction or in bearing. And then the second consideration is if it is laterally loaded pile. There's a third consideration, but it is only applicable in colder region, like in North America, probably Australia, New Zealand, in some countries in Europe, um, Russia. So in colder regions, there's another consideration, and we will discuss about it later. So it is called frost jacking. And this is due to Adfreeze, but we will discuss that later. So with regards to pile capacity, so for piles we have to, like, if this is say cast in place pile, so we have so if this is your load, then this is your total capacity. So your capacity is now, if you remember, um, in school, we were taught about capacity based on skin friction, right? Skin friction or shaft adhesion. The other term for this one is shaft adhesion, and then the other one is or number two is end bearing. So shaft adhesion or skin friction, that would be your capacity based on the skin friction along the pile length, right? Which is equal to the pi times d. So that's your pile perimeter, and then times L. Your L is the embedment, and then so that's your surface area, pi times d times L, and then times the skin friction. And then in bearing, of course, that is your pile area, which is pi times d squared over 4 times bearing capacity. So that's your in bearing. Now, in school, we were taught that to get the capacity, you have to add these two, skin friction and in bearing. But in practice, um, geotechnical engineers don't recommend to add those. It's either skin friction or in bearing. You don't add these two. Now, with regards to um, minimum embedment, of course, So if you are using in bearing, so if you have your, if this is your in strata, so this is like a good soil. So you have, say, this is soft clay, and then on second layer you have, so this is layer one, layer two, and then say 6 meters. So this is say 6 meters and layer, then this is 3 meter layer. So total layer is 9 meters. But within this strata, you get a good, bearing capacity. So what you can do is you will design a in bearing pile. So this one. So this will be in bearing if the soil is really good, especially if it's like bedrock, or sand, then you can do in bearing. But the downside with sand, if you go in bearing, is it might slough. So you will end up probably using a you will use a casing. The same issue with you have if you have groundwater table. Now for bedrock, so if this is, for example, this is bedrock, and then if you're in if you are using in bearing, if this is only just pure eggshell, then all you have to do is basically try to reach the good strata. And then this depth, most geotechnical engineer would recommend this embedment to be equal to the whatever is the diameter of this pile. You you know um, embed that pile equal to the good to the wither bedrock. Then that is already enough for embedment. Or if this is a build pile, we already discussed this one. If this is build pile, then this depth would be at least equal to the build diameter. This one. Now, if you are using skin friction, of course, it really depends on, what's the demand. So if that is, if you have 2 layers, and then your pile is this one, right? And it's subjected to compression load. So if you have two different layers, then all you have to do is just sum up this one, right? Sum up this skin friction. Now, this one is already known. Say, for example, this is 3 meters, and then this is 6 meters also. But you don't need total of 9 meter embedment if along this depth you have enough capacity. So, for example, this is H, right? Now, all you have to do is just divide if this is load P, then your capacity would be the capacity of this layer 1, and then the capacity of layer 2, which is with respect to H. But this is known, so the only unknown is H. Then you will get your total pile embedment. So that is if it is what we call this one, if it is pure axial compression or uplift. If it's uplift, then it will be the opposite. Now, if it is laterally loaded, that's another story, because what will happen is if this is your 2 layers, and then this is your pile. Now, if this is subjected, it depends. If subjected to a really large lateral load, then there's a tendency that if your pile is too short or too shallow, what will happen is it will tilt like that. Now, to do this analysis, there is a software called LPile. Now, LPile for single, and then group for, of course, file group. And this is by InSoft. So I started using this software in 2014 when I joined another company, and we were like foundation design consultant. So I started using this one, and it's really easy to use. Just input all the value. So I have a sample calculation here. I just edited all the information, so um, you won't see my um, name and information, company information, because all of this you have everything will be shown here. Yeah. Everything will be shown here with this model we prepared by, and then you have the information, description, engineer. But what will I show you is first, I because I did uh, three different um, three different embedment. So this is the now. So when you run the analysis for L file, you can try different embedment. So at first I tried this one, 3.4 meter embedment. Now, if you notice, this is your origin, this line. See, that's 0. So this is negative, this is positive. Mm. Now, if this is assuming this is the load is in that direction, no, going right. Now, if you notice at 2.8, more or less 2.8, there's a point of inflection or point of rotation. It rotates at this point here. And then if you notice the bottom of the pile is on the left side of your origin, that means the pile is rotating at this point. Now, if this stays on the left side of your origin, that means if your pile is subjected to lateral load, there's a tendency that it won't go back to its original position. Now, so in this case, this is not good. Now I tried another embedment. This one, this time this is 4 meters. Now still the same. This is our origin. If you notice, the bottom of the pile is on the left side of the origin. So that means the pile is also still rotating the end of the pile or the bottom. Although this deflection is really small, like 1.2 millimeters. Although, I mean, technically it's fine, but if you look at this elastic curve, you know, at 4 meter embedment, there's a tendency that um, the pile being subjected to the lateral load, it won't go back to its original position. And then if for some reason your structure, the any translation is critical, then you won't allow this one. If it's just, freestanding, say, if this is a light post and you don't really care if, like the post is tilting by 0.001 degrees or whatever. And in this case, the deflection is 0.002 meters. That's zero point 0.2 millimeter. That's really small. So that's nothing. But if you are concerned about possible rotation, and if it rotates, it won't go back to original position, then this is not enough for meter. So in this particular project, the embedment is what I did is I used 6 meters, but the explanation is if you notice, this is our origin. Now at 3 point something, there's a rotation here. But somewhere along this line, between 5.5 probably or around 6, it go back to the positive side. That means there's a second point of inflection. And if this pile is subjected to lateral load, the tendency, because it's not rotating at the bottom, then it will go back to its original position. Now, this is just like when you run the analysis, you can have a look like really quick at this graph. Just click, there will be a graph on the side, and then you will just click it. But the actual calculation, this one, so this is the actual analysis. So you will input all the, shaft diameter, all the information. The good thing with this software is now this is a cast in place pile, but this software can run steel, or concrete field, steel pile, square, round pile, precast, cast in place, so it can run any, like, almost all piles. So um, this is, I mean, um, I think 1,200 a month. Can't remember. But after I experienced using this at the other company, when I joined back from, like, to where I work now, I really convinced them to buy this software. Especially we have a geotechnical department, so I convinced them to buy this one. So ever since, um, I've been using this since 2014. So this is the so at depth. So you have bending moment. You know, uh, so the deflection. So these are my loads. This one is really small because this is a um light post. So this is a light post. So if you notice, the gravity load is really small, but it's the moment that's critical, the big one. So this graph you saw earlier, this one, this graph here, the calculation is this. So like I said, the pile deflects to the right because the load is direction of the load is to the right, and then there's a first point of um, inflection at 3 meters, so it's negative. I don't know why there's double negative here. I probably let's see. Yeah, it should be just one. So anyway, if you notice at 3 meters, so you have your first point of inflection. It changed from positive to negative. So that is this graph here. So at 3 meters, so from right, it changed to negative. So that is to the left. And then it will go back to positive again at 5.28 meters below this one. So that means your pile is basically, if this is the origin, if we will exaggerate that one, the pile elastic curve looks like that one. So this is at 3, and then this is at 5.28. Now, technically, since this one already crosses the origin again, then you could, terminate your pile at this depth. But I usually round it off to a whole number. So instead of 5.2, I could use 5.5, but I just use 6 meters. And then if you look at the value at 6 meters, it's positive 2.15. So that's really small displacement, but um, at least it went back to the positive again. So that means if the pile is loaded laterally, subjected to lateral load, then it will possibly going like go back to its original position. So that being said, if so for compression only, then you have this calculation, and then for lateral loaded pile, you will use this um, graph to determine what's the minimum embedment. Now, on this one, I would say 6 meters. Now, for example, in the first solution, like due to vertical or uplift load, your minimum embedment is, say, you need 6.3. And then due to lateral load, you need at least 6.0. That means your required pile length is 6.3. But if this is only, for example, for the sake of discussion, this is only like 5.3 meters. And then due to lateral load, you need 6. Therefore, your minimum embedment is 6 meters. Now, earlier I said about a third um, consideration is frost jacking. Now, in cold climate, the pile will be subjected to, so if this is your pile, you have your layer. Now, geotechnical engineers would usually, I mean, at least in this area here, geotechnical engineers will usually recommend between 2.1 to 2.4 meters. This is called frost zone. So that is called frost zone. Now, in this area, the pile will be subjected to a huge uplift force due to frost that is called the Adfreeze. Due to Adfreeze, and it will result to frost jacking. So um it will be subjected to like an uplift. Now, the value of this Adfreeze depends on the type of pile. If it is concrete, if this is concrete pile, this is usually 65 EPA. And then if it is a steel pile, the value is at least 100 EPA. Now, say this is 2.4, usually, I mean, between 2.1 2.4, it depends. Some geotechnical recommendation would say 2.1. And then any screen friction within this zone will be neglected. No, it will be equal to 0. Now, the actual or your final capacity would be any skin friction or shaft adhesion below the frost zone. Now, for the sake of discussion, say you're using a steel pile which is 100 kPa, and then your bearing or your skin friction is, say, um, 40 kPa. So this is your skin friction right here. Now, all you have to do is basically by ratio and proportion, you can say 200 times, say, 2.1, and then 40 times whatever is the H. And this force, this is ultimate. So that means your skin friction here will be the ultimate. You don't apply any geotechnical resistance factor, or you don't use factor of safety, just use the ultimate skin friction. So, for example, this is what, 40 times 2.1. So that is 80.4. So that's 80.4. And then this one is 100. No, 100 divided by 80.4 is 1 meter something. And then you add that to 2.4. So that is your, um, well, this one I am assuming this is uniform skin friction. If it's, you say, different layer, different soil profile, then of course you will use the appropriate. But basically that's the general equation. So um, oh no, not 40 times 40 times to 100 times 2.1, and then you equate that to 40, and then the height, whatever is the height required. So basically 200, 100 times 2.1, that's 210 divided by 40. So that's what, 50 something or 5 meters. So 100 times 2.1 divided by 40, 5.25, 5.25 meters. And then you add that one to your whatever's the frost depth, depth of the frost zone, which is 2.1. So this time this will be 7.35 meters. Now, in your original calculation, you have say 5.3, 6.0. But for frost jacking, you need 7.35. Then your minimum embedment would be 7.35. So it is deeper than what's required for axial load and what's required for lateral load. So that's, frost jacking. So it really depends on how good the soil is. The bigger the skin friction, the shorter the pile. So at least that's the calculation. And in this frost jacking, if you have uplift load, if you have uplift, this is separate from the uplift. You don't add this to, although this is upward, but it is a different mechanism um, from the uplift load. So you don't add those two. So if you have uplift load, then you check another consideration, which is uplift, and then you determine what's the required length due to uplift. Then you have your fourth value, and then you choose between like which one is larger of all these embedment required. Now, with regards to driven pile, it's different because um, it depends on your usually driven pile. The criteria would be drive to refusal. So um, the criteria for fusel is, if I remember correctly, is 10 blows per inch to for the last 10 inches. So 10 blows per inch for the last 10 inches penetration. Now, if I've seen this like in many um, foundation drawings, but this is only efficient if the your pile loading is like the range of the load is not like um far apart. For example, you have 10 piles, and then your load is say uh 30 kilonewton, 31 kilonewton, 35 kilonewton. Now if this is your loading, like close to each other, like, then you can just design one pile, and then you say, okay, drive to refusal. But in some, for example, in our project, we have a shop, and then it's a pre-engineered building. So if this is your foundation plan, so of course you have your frame right here. Now these piles, you would expect a large load on this one. Sometimes it depends on the span, but most of the time this ranges between 90 to 120 kips, or 90 to 120,000 pounds. And then for your end wall, like right here, you will only see like, you know, it's even less than 10 kips sometimes for your end wall. Now, if your criteria for these piles, like end wall piles and this main frame piles, um, if you use the same criteria, then this will be really uneconomical already, because just imagine you only need about 10 kips capacity, and then you drive the pile to refusal, it could be larger than 120, so that would be overkill. So the efficient way of providing the um, what we call this one, the blows per inch, the pile driving criteria is now the theory for pile driving is, if this is your pile and this is subjected to an energy equal to the weight times height, the weight of the hammer and then height of drop. So that would be your energy, that would be equated to your capacity at the bottom times the penetration, which is S. So, the bigger the energy, the bigger also the penetration. That's why if you try to pound a post for your fence, if you are using like just a stone, you will hammer this one with a stone, say the same size as a baseball. Um, but that's only like about 3 inches diameter. Versus if you will use a large chunk of boulder that says 12 inches diameter, then of course if you try to hammer your fence with this large boulder, it will penetrate more compared to a smaller stone. So that's the theory about driven pile. So the larger this one, the bigger the driving energy, the better for the pile to penetrate the ground. Now, for driven pile, the formula is, I mean, there are new formulas now, but the accepted criteria or formula before, even today, I'm still using this one. I mean, um, I could use other formula, but it's been like, you know like a while, like probably like more than century. This formula has been used. I don't know how long, but this is direct. You know, your P times S is equal to WH, or therefore your P is equal to WH over S, and this is your load, or this is your capacity. And then usually just divide this with 6, because the factor of safety of this one is 6, and that is your factor capacity. Now, this is, I think, plus point 1. This point 1 is if this is a diesel hammer, I think. It's been a while since I designed a driven pile. So there's a constant here. I think point 1 is if it is diesel hammer. I can't remember. Diesel hammer or drop hammer. But technically, to determine the penetration is you have your S is equal to WH over P minus point 1. So point 1, that's really small. So let's just disregard that for now. So your general equation is H is equal to WH over P. Now, W is in pounds or kilonewton, and then the height is in feet, right? And then your P is in pounds. Therefore, your unit for S is feet per blow. So the unit of S is feet per blow, or you divide it by 12 or times by 12. So that would be inches. Say if this is 1 for the sake of discussion, that's 1. So that one foot per blow, or 12 inches per blow. That one. But usually the penetration is determined in blows per inch. So all you have to do is your penetration is just divide this, or do the inverse. So that would be 1 over 12. So that would be one blow per 12 inches. So this is your penetration or your pile driving criteria. So that's why it depends on the load. It depends on how much is your um, um, load, then you will calculate for the S. So if this is just 10 kips, then this will be small, right? Or this will be big. But since you do the inverse, then that would be a really small value compared to if this is divided by 120, and this will be really small. But since if this is decimal and then you inverse, then that would be a large value. So that's why that's why this is 1 blow per inch. But for large pile, this could be, you know, 5 blows per 3 inches, something like that. So yeah. So that means this one will require more blows per inch of penetration, so that because this is the capacity or the target load for this one is larger. So that's why or at least to me, when I do driven pile, I will have a pile driving criteria. So for example, I have 5 different pile types: P1, P2, P3, P4, and then I will have, you know, driving energy. Usually, driving energy, it depends on the weight of the hammer. Now, you determine what's the minimum weight of the hammer, then you will just adjust this one. So, for example, your height is, or this, your weight is, say, 10,000 pounds. Now, if you want 20,000 pounds, then you just i- use a height of equal to 2. So, this would be 20,000 pounds, foot-pounds. Now, if you want, so for example, for P2, you need 30,000, you use 30,000 of energy. That means you raise your hammer 3 meter or 3 feet from, so this is your pile, this is your weight W, and then this is your H. So if you adjust this one, then you will increase the energy. And then this one, for example, if you are using the same energy, 30,000, you can use the same energy, but it will differ in the blow counts. So say for example, this is 1 blow per 12 inches. This one is say 3 blows per 12 inches. This one is 5. This is say 10 blows per 12 inches, something like that one. It really depends. So that's how I um, do a pile driving criteria. But like I said, I've seen a lot of foundation plans where they just specify one uh, criteria, which is drive the pile to refusal. And if that's the case, it's gonna be really expensive. If it's just like, 1, 3 piles, 5 piles, then that's fine. But if you are talking about, I've designed a project like almost 2,000 piles in one project, all driven piles. So if you do, like the same criteria for 2,000 piles, more than 2,000 piles, then imagine how much it will cost you. But if you at least group the pile and then determine the actual blow counts required, the number of blows, then you can save a lot of money. Um, because if you drive to refusal, you will end up probably driving a P1 that requires only 18,000 pounds capacity, 10 kips. You will probably drive this to what, like 30, 40 feet just to hit the refusal. But technically, you only need like about what, 20 feet. So it matters. So anyway, so that's for driven piles. And then, of course, you will equate that with uh, the capacity, at least to get the minimum But usually for driven piles, we don't even need, or we don't um, require, or it's not necessary to get a um, soil investigation done if you are using the driven pile. That's the advantage of using the driven pile. Also the screw pile. So for projects where you know um, there's no soil report, we don't we don't specify, or we don't recommend concrete piles like cast in place, cast in place piles. This is not recommended for project, or for project without soil report, because there's no way you will at least estimate, you can estimate the capacity of your pile unless you do a pile load test. That's fine. If you're open to do, pile load test, then you can the problem with that one is, what if it fails? I mean, you can just, splice a concrete pile. I mean, you can, but it's not really um, a good way to increase the capacity. But if there is no soil report, we usually recommend screw pile and driven pile, because these two the pile types, you can estimate the capacity. So for driven pile, you can estimate the capacity based on the blow count. No, so um, yeah. So for our projects before, um, sometimes if it's like the depth or the pile embedment is ridiculous, you know, say you already up to like 60 feet, and then you still don't achieve the refusal. So they would ask you, or they will ask me, like, is this blows, like blow counts, okay for this pile? I mean, the length is really deep now. So I would say that's why I don't really specify a driving criteria that is driven to or drive to refusal. I always provide a minimum blow counts. Now for screw pile, you can also estimate the capacity of this one based on torque lugs. So when they install the pile, they will give you a torque reading, because this will be, I mean, by the name itself, screw pile, it will be screwed to the ground. I already posted a lot of information on this one in my page. But the good thing with this one is you can estimate the capacity using torque reading, and then using the torque correlation factor, KT. Now from this one, based on torque reading and then the diameter of the pile, you can estimate the capacity of the pile using this value, torque correlation factor. Um, I mean, in the Canadian Foundation Engineering Manual, there is a recommendation for torque correlation factor depending on the type of, or the size of the pile. So you can determine the capacity, or at least you can estimate the capacity. So that's the good thing with, like, for projects without soil report. But if you do have a soil report, then of course you can use the cast in place piles. So yeah, I think that's it for today. And if you have any question, just write it in the comment section. So that is how you determine the minimum embedment length of a pile. So okay, till next time.